So the slides are online here. Slides.unsupported.io/explore and Strace. Not proc like yesterday. So the slides online are just a slightly bit outdated. I forgot to add the bumpers for LinuxFest Northwest, so I'm gonna use a local version so the video can know where to stop and start, if you will. Full screen. There we go. But if you follow along online, some of the words might be different, and later on that URL will be updated with today's slides as well. Alright, so LinuxFest Northwest, start the recording there. This is your system calls in you, a brief exploration of using Strace. So that's the right room, you're in the right place. Usually, like I said, if you saw my presentation yesterday, always like to start with hello. Kind of keeps me at least on track. So hello, again, my name is Alex. Hopefully you all come and say hello later on at the end of this. When I first did this presentation, I wasn't sure if the audience would resonate more with Lionel Richie or Adele, so I put both up there. So some people get some people get the other. And also, thank you. Again, as always, it's a privilege and humbled and honored that you all choose to spend time with me today through this presentation. Like, there's a ton of great talks going on through the entire conference, so as always, just thank you very much for choosing this talk. All right. So our agenda today. First off, why this topic? I always like to go over and set this groundwork for why choose a certain topic. Again, all my topics are really kind of back to basics or kind of bare bones topics. So I want to make sure that I set the stage of why it's important, why it matters, and where we're going with that. Then we'll go through what is Strace. Okay. Then we'll talk about system calls individually. We'll go through some of them that I find most important, most useful to me as a system administrator. And then we'll go through how to find out more about all the other ones out there. Because it's great to show a few of them, but if I can't show you how to find out more about others, then I've kind of lost on only the first 4 or 5. We'll go through some demos, and then we'll go through continued learning, or how to take away something from this presentation that you can take back out to your home computer, your setup, and continue learning about Strace and different processes. And then if we get a chance, we'll have a chance. We'll do Q&A. Okay. So why this topic, right? Why choose a topic that is one program? Why talk about that for 45 minutes? It's about 2 major things. The first thing, it's about being able to solve problems. I work in a managed hosting environment, and with that, all of our customers get to run their own setup. They have root. They can install whatever they want, whether it be the latest and greatest monitoring or nothing at all. And as admins in that environment, we need to be able to troubleshoot anything on any system anywhere. So while some people have a full setup for maybe New Relic or App Dynamics to kind of monitor everything, really some people don't. So I try to teach applications you can use almost on any system that's available on almost any system, and really get down to the core of what's going on. That's why Strace comes into the picture here. It allows us to really dig deep down, no matter what system we're on, to see what the problems might be. Okay? And then again, it's back to basics. It's about being able to troubleshoot almost anything, anywhere, with just the basic tools, and really understanding what those more advanced tools are doing, or maybe doing, to kind of get you to understand that really core portion of what the system is doing. Okay? And we'll go through some examples of the way when we used it to teach other techs, or I've used it myself to kind of solve problems for our customers. So, what is Strace? In this section, we're going to cover 2 major things, right? What does Strace do, and how to use Strace. Okay. In this presentation, I'm going to go through quite a bit of terminology and jargon before we get to the demos. I want to make sure that we have the same base before we jump into the demos and kind of see what's going on there. So what does Strace do? Very simply, Strace interrupts the process and it intercepts the system calls. The system calls, well, let me jump next slide here. All right, I introduced the term system calls. So what is a system call? A system call is just a function that's provided by the kernel or exposed from the kernel to the application itself. In many languages, such as C or Python or anything, we write code in that language. That language gets interpreted to what the system can understand kind of at a base level. So what it all comes down to is simple functions such as an open or read or being able to malloc memory or allocate memory out. All code goes down to those basic functions. Even further down if you want to talk about assembly, but kind of at that base level comes down to a few simple functions. Okay. So real quick, we're going to go through a few examples of how to use strace before we jump into the demos. But really, it's simple. We can use strace to wrap around any application. In this case here, just a quick W, right? Who's in the system? It's as simple as that. We can go a little further. Well, here's an example output, right? Again, this is, I'm not sure if you can see it that well. We'll do some demos, but if you have it on your screen, you should be able to read that there. Mostly more for reference later on. But if we want to get a bit more verbose, like any application almost, we can add -v and get more information on that. Bless you. About the output there. And the output looks a little more in depth as we see here. One thing I do want to show, if you can see this screen here, is from this one here, that first line. It's a bit shorter. It kind of compacts all of the variables that get passed through in our environment. You see right here. We have our command W, and it says 17 variables there. As we do verbose, we get to see what those variables actually are. What environment variables get passed to your system. Okay? So again, we get a lot more, strings a bit longer. Again, it's just a bit more information. Okay. I use this usually as a first run. If I can't find what I'm looking for, I'll take the -v off and kind of just begin to parse through the slimmed down output, if you will. Not only can we use strace to run an application directly, we can also use strace to interrupt and attach to a currently running process. This is probably the most useful to us when we have something like maybe Apache or an application that's already running, a server that's already running that you don't want to restart, but it's not acting quite right. So we can attach to a currently running process and begin to start interrupting it right after that. Okay. So with that though, a quick warning. What's actually happening when you do an strace is that there's a sig trap sent to your process. Now some processes, well most processes, will take that sig trap and begin to give back what's going on. What are you doing? I'm doing this. What are you doing? I'm doing this. What are you doing? I'm doing this. But some processes don't like that. If, for example, you had a proprietary process that you're paying a license for, or you have, kind of, they don't want you to see what's going on, they could do sig trap. It's blocked. You'll get a sig stop after that. So what that means, you have a process that is running along, it's just fine. Then it's like, oh, hold on, it's a trap. Stop. And some processes will begin to either crash out, tell you can't do that, and close out, right? Because all it's doing is taking a signal and saying, hey, strace is saying, hey, what are you doing? The process is like, no, I don't want you to know. I don't want you to know. I'm going to stop. Or here's the message back. I'm quitting. Or it crashes. Okay. So keep that in mind. If it's a process that you absolutely is not acting right, but it cannot crash, maybe there's other ways to do this. Ltrace might be another way to do this. But again, it's one of those things where it's very rare. In our environment, we have maybe one or two processes that we know do this, and so we know to stop that strace those. They're mainly installation processes. Right? They don't want you to see kind of the how the sausage is made, if you will. Okay, so with all the output that comes from a process, it's ideal to save it to a file. So you'll go back and look at it later on. So we can do that with -o. And -o within the file, and then whatever process, whether it be a PID or process right after that. We'll see a demo of this in just a bit. Oops, wrong way. There we go. Okay. Probably in the form I use most often is this here, -ff-o. We can use strace to not only follow a process, but we can tell it to follow a single process and then begin to follow every child process after that. Okay. In our case here, mostly in my case here, I think about Apache. I trace the root process and then see what every individual process is doing right after that. We've used this in the past where we've had Apache. We've noticed that in the error log, just PHP fatal error over and over and over and over. And so we're talking about just hundreds and hundreds a minute. What we did is we strace that root process in an example like this here. And what that does, it outputs out individual files. So it might be file.pid number. And so you'd see it, and you'll see a demo here of it later on, but you'd see Apache attached to all those processes and immediately detached because it died. If we look at the last line of every single one of those files, it was open certain files, something PHP, sig fault. Hey, Mr. Customer, what'd you do with that file? Oh, we changed X, Y, and Z. Change it back. right? Did that, and it worked, okay? But we could tell from the process was opening a file and dying every single time. And it was real evident at that point to say, hey, go back and change whatever you did here. That's what the output looks like there. You're going to get for example, if this was -o HTTPD, it would be HTTPD followed by the PID number. That's what example of the output there. And we'll see this again later on. Okay, so not only can we use Strace to just vomit out, vomit's not the right word, display out all of the system calls, we can also get a summary. So strace.c to count up all of the system calls, and it looks something like this. We might use this when we're not sure where to start looking at a process. We know the process isn't working quite right. We know it's doing something we should be doing, or it's kind of funky. We'll do something like this to look at it first and say, well, if you're spending most of your time in opens here, well, let's begin looking at just the opens. Or if we're spending most of our time statting a file, well, what file are we statting all the time? Okay? And we've seen this in the field a couple ways where a process is just taking longer than it should, or we think it should. We find it's spending a lot of time in opening files or statting files that aren't there. And we'll see that again in our examples. And then lastly, we can get how the process was exited. Usually we should see something like this at the beginning, or at the end, sorry. Like exit was 0, everything was good. Sometimes we don't. Sometimes you see that it was killed somehow. Sometimes it's a seg fault. Okay? So we'll get that as well. Kind of at the very end of the process, what happened? All right, so system calls. In this section, I want to go through some of the more common system calls that I've come across, or the system calls that you might need to kind of get a base on before looking at output. These are kind of the most basic ones that all applications are doing, right? Opening, reading, things like that. We'll go through these first, we'll go through them, and then we'll do demos. So, just to reiterate what is a system call, again, it's a function that's provided by the kernel out to the interface, or the application interface. Okay. Real quick note on system calls. They all follow pretty much a similar format as far as you can see in the output. The first part is a system call, which you see right here. Then followed by any arguments you might have in here. And then the return value. Okay? And that return value, what it means is going to be determined system call is system call. By reading the man pages, we can figure out what each part of those means, what we can fit in the arguments, and what the return code means. In this case here, you'll see later on, read basically means the return code is how many bytes were read. Okay. Okay. All right. So, again, we'll go. Question.
It was showing us the buffer we're passing in to read.
Mm-hmm.
Are the contents of the buffer that it's displaying after the call completes or before the call is made?
It is after the call is made. What read in.
Okay. So in the case of read, it's what we read in.
Mm-hmm.
Okay.
Yeah.
Cool. Thank you.
Yep. So. All right. So, open. Basically, open up a file or device. Okay. Here you get, what I'm doing here is kind of how it's constructed. As baby sysads, we don't need to know so much about it. As developers, probably know more about it than we do. But really kind of give you an idea of what's going on. So in this case here, we're opening, right, giving it a path name, giving flags, and the mode we open it in. Okay. So, and then giving a path name for file, open returns a file descriptor. Again, that's from the man page. We'll see here in a little bit. The read. Okay. So we're reading in. We get the file descriptor we're reading from, the buffer we read in, and then the size that we expect to read. Okay. On success, the number of bytes returned. The number of bytes read is returned. Okay. So, if, for example, if these two didn't match up, the number of bytes you want to read and the amount of bytes you actually read, those don't match up, well, then maybe you reach the end of the file, right? Or something else was wrong. fstat, get the status of a file. Okay. Think about reading the inode of a file. Okay. Get information about that file itself. So, given a file descriptor, looking at what structure for we have, your inode, your mode, things like that. Or mode being the permissions on the file. The memory calls here, right? Calls to map memory or unmap memory, right? Allocate memory or free up memory. We're going to see those quite a bit. I've seen in the case where we saw a process just continually just mallocating memory, just trying to map memory over and over and over for no good reason, it seemed. That could just it would take up gigs of memory, and if you looked at what was trying to read in, not a whole lot. Okay. All right, so I've gone through some of the most common ones, again, that we see and you're going to see almost with every application. But there are about 441 other system calls out there. I pulled this from looking at the man pages, which I want to talk about for just a second here. Actually, let me switch to terminal real quick and do this. Man. One thing to know about the man pages is that usually when we do man in a command, we get man page up. Some people don't necessarily understand or know that there's different sections to a man page. And if you look at the man page for man pages, we'll see the different sections here. Okay. Most of the time, you're going to get something like 5, right? Section 5 or Section 8. Section 2 is system calls. Okay. I make note of this because if we did a system call, for example, not that. Where'd you go? There you go. If we did a system call for man read, by default, it would pull up the bash built-in or the bash man page for the built-ins. Not what we want. By specifying man 2, then we get the section of the man page that refers to system calls. Okay. So sometimes, because sometimes some functions, some programs may have the same name as a system call. Okay. So make a quick note on that. Again, as you go look for more of them, right? You're going to see that sometimes they bring up what you expect, right? Where it looks like a man page or a page for a system call, or you might get something that looks like the man page for a different application. Right? Okay. And real quick, how I pulled that number for 441. If I go to user source, where'd it go? Did I keep it here? Share. There we go. Thank you. Man. And then man 2. Right. Looking at that, I pulled the number for 441 or so. Might be different on this system itself, but let's see here. 428. Yeah, so I forget what distro it was I pulled the number from. But that's how I pulled that number. Right? How many different system calls are out there? Some of these are synonyms for other calls, so it's not quite that many, but there are a number of them out there. Okay. All right. So now demos, right? The part that we all wait for. First demo here, Strace W. Real quick, I'll make a note that, let's see here. If you don't see it refresh on your desktop or your laptop, I include a video of kind of the output here. I do that because, not because I expect you to see this here, more as a reference point later on if you visit the slides. If you're on your laptop or phone, it should show up in fairly good quality. I understand in presentation format, it's not that great. Again, meant for viewing them later on. That's why we have live demos here. So Strace W. Okay. Again, kind of the most basic way to use that Strace here. And we'll do that here. Okay. Again, real quick to notice, we'll do from the bottom up how the program was exited, like we saw earlier. All the different system calls that it makes. Right. Just kind of give you an idea of how many lines there are here. That's not what I want. Pipe. Oh, that's right. 2 and 1. I think that's right.
2 greater ampersand 1.
Thank you. Yeah. 931 lines out there. Quite a bit, right? So, again, Strace W, and then that's not going to be there. So, see, everything comes out through here. So again, if we want to go ahead and save that real quick, strace-o, we'll say w.out, and then we'll say w. Then we'll get the output of the command itself with everything being directed into that file. I'll take a look at that from here. Okay. Now it's a bit easier to look through. Notice I see up here, right, without the -v, we get some of the lines that are just compressed together. Let me go ahead and let me switch back here a second here. That's for W. Oops. And then go down to C. Right, so look at the system called itself, strace-c. Let me start. W. Okay. And we see that strace or W spends most of its time in open. Okay. Very little time in anything else. Again, W is just a very simple command, nothing that we expect to be nefarious or giving us problems, but just as an example of what's going on. Okay. Let's see here. All right, we've already done with -O. Okay. Real quick here. Also, if there's a program, I use password in this example here because -O. If there is, input that we need to give it, I can still trace the process with all the output not getting in the way, right, and be able to send it into a file. So, change the password here. Okay, and then if we look at our file, we have, right, the output there. If we didn't do that, right, if we just did strace password, right, we'll get everything up until it decides to read for us. Okay, then we would type in our password. And then we go through. Not easy to read, not easy to go through. So if you have something you're tracing that you're not sure what it's doing or want to figure out more about it, you can give it that -O to kind of put everything in the background there. Okay. Let's see here. And into your question there about reading in, if the read command was what you're reading in, it pulls that in and then puts it out into the output of strace. All right, get a little more deep into the examples here. We noticed earlier, real quick. Let me show this real quick here. We do the strace -C and we'll say W, right? Do that. Okay, we see that it's been last time was open, some it's stat. We see that a lot of times we can figure out where it's spending most of its time. Let's say that again it was open. Read. Yeah, okay. We'll go with this one here. Let's say that we see here it's spending 100% of its time in read. That's fine. Let's do this. We can go through, and what this part here does is I'm tracing a group of operations at this point with -E trace equals file. I can do that for file, I can do for open, for reads, for memory, things like that. Because 931 lines is not fun to look through, right? But if I know there's a problem with opening a file, I can do it just to that. So, real quick here, let's do this. I'll just copy this one as it is and do that there. So strace-E trace equals file. Again, if you look at the man page, there's a ton of families you could do. I think file, break down to reads, opens, and then I'm putting out the output. I'm putting the output to password-trace.out and then running the password command. Okay. Let me see it there. We look at we see we get things only that have to do with files themselves. Okay. So only opens or stats, reads, right? We could change that and say maybe I just want to do things with reads. And all reads. Okay. Again, just limits the information we get back so we can better understand exactly what we're looking for. Okay. You may notice a lot of these lines are a bit condensed, and we can go a couple ways to make that a little more verbose. Again, with a -V. Okay, so we get a bit more verbose here if we look at the very top here. Where'd you go? We get a bit more verbose, but also a lot of these lines may be cut off. Okay, so we see here. We can go ahead and make these lines full by giving it the, now I'm forgetting it. I think it's -S for string size. We'll say 4096. There we go. And just by doing exclamation and then less, I'm just running the last less command I ran, as we see here, to less that file. Now we get the full output of that string size. Okay. Question?
So the classes are not mutually exclusive, right? When you did file, we had some read operations too.
Mm-hmm. Yeah.
Okay.
Yeah. We have the operations, but we're getting those back on standard out just because we're not seeing all the output for it. Right? Make sense? Answer your question? Okay. Bless you. Okay. Amount of time. Again, a lot of these demos have small videos with it. If you don't see them the first time, just hit refresh. For some reason, they don't show up all the time. Question?
So, these can potentially have sensitive data, right?
Potentially, yes. Yeah. Potentially, depending on what's being read in. If it's unencrypted from the disk. Yeah. That's very possible. Yeah.
I can trace your bash and see every keystroke you push.
Right.
If you're the administrator.
Yeah.
Well, right, but my point is when you're going out and asking for help and people say, can you post an S-trace? You're going to need to do some cleansing, correct?
Perhaps, yeah.
Depends on the arguments you pass to it.
Well, sure.
The arguments you pass, or yes.
Or if the programmer reads files that.
Essentially, arguments from the process you could get out of the proc as well. So,
All very true.
The ASCII table memorized knows what root password you
That's why it's a local machine. I've learned better. I did this demo on a cloud server once. Just a server I had out there, and forgetting that it was a server that wasn't local to my box. Simple password, Red Hat. Come back to the box about an hour later. I'm like, why can't I? Oh, damn it. Blow the box away, start over. So, all right. Let's see here. Is this the last one here? Yeah. How are we doing on time? Okay, I think we're good. Okay, so one more demo here. And this is a fun one because this is one I've used many times in my day-to-day work to solve problems as well as to show techs have really being able to dig deeper into what's going on. Let's set the scenario for you. Scenario. We had a customer who had their Apache's document root stored on NFS share for all their servers to access at the same time. While not advised, it worked. Worked fine for them. Worked fine for them for many months. All of a sudden, it didn't work. What'd you change? Nothing, right? And we go to that back and forth. What'd you change? Nothing. What'd you change? Nothing. We go back through the tickets and we see what's that? What's that?
No, really, what'd you change?
Yeah.
It's like, yeah.
No, nothing, right? Except what they did change. Bless you. What they did change was there was a ticket put in because technically we changed it for him. They didn't change anything. There was a ticket that they asked us to enable htaccess files for Apache. For those unfamiliar, htaccess allows you to allows the user to configure certain parts of their application or their Apache processes to do certain things, whether it be rewrites locally in a directory, right, without having to modify the entire Apache config, or have elevated privileges to modify the Apache config. Works great in shared hosting. Works great when you have developers you don't really trust, things like that. But you have other problems. You have developers you don't trust. You have way more problems over there. But that's a scenario here. So turns out they were like, well, that couldn't have affected it. We changed that and it shouldn't affect anything. Well, they just showed them that it did. So that's my favorite scenario here. We'll hop back on my box here and kind of walk through a setup of what that looks like. And the thing about htaccess files is that when you enable them and you hit a file in a directory structure, Apache has to check for that file in that file directory and then every directory up that path. Okay, and the way they organized their directories was very long, just for their organization. Okay, so real quick here, let's do this. I'm just going to show you what I did as a small change, so you know, for this demo purposes, here's a few things I changed. For the purpose of the demo, I changed these two variables in Apache's main config. Start servers for 2. Again, I only want to start a few. And then the max request per child down to 10. Okay. What this directive does says, hey, after 10 requests, close down that thread and spin up a new one. Okay. I'm doing that just for illustration. On that server, I think it was much higher, and all these values were much higher on the servers themselves. So again, this is just for demoing purposes. Okay. So I have Apache running, and that's great. What I'm going to do is attach to the root process of Apache here. in much the way I showed in that format there. strace-ff-o, a file name, and then P for PID. Again, FF is to go through and not only trace, not attach only, not only to the parent, but then begin to trace every single child after that. Now, we see Apache here running with a few children already. What's not going to happen is that strace will not attach to these children. It will attach to every children after our command. Okay, that's why I have the fast refresh on that, so I can see those attachments happen right afterwards. So here our demo setup here. We'll say strace-ff-o, and we'll say temp, and we'll say httpd. It will append every file there with the PID number afterwards, and then we say P for process 1256. Okay. Yeah. Okay. So what's going on there? Real quick, I'm gonna hop on to profiles, light background. Okay. Yeah. Well, true. Again, just to generate. Oh, really? There we go. Again, I'm just hitting my local server over and over and over. What we see here is that our processes are being attached, right? And I'm just spinning that web server over and over and over. We don't need much of this. Let's Control C. Cool. We go to temp, and we see all our processes there. Now, if this was Apache crashing, again, like I said, at the end of every single file, we'd have the file it opened, or the reason, for the most part, the reason it crashed. Okay. But in this case here, we see that, I'll just pick one. Any of these will work. Everything going on here, right? So notice here, very simply, index.html. So we do a stat on the directory, have to look for the .htaccess file. Not found, right? So again, it's a wasted call right there. Okay, and then index.html, we open it, or we stat it, we open it, and move forward. That's fine. That's what usually happens. Let me close this off here. Now, to kind of simulate a long directory structure, under this directory here, we have 1, 2, 3, 4, 5, 6. Right. So, and this is, while it's maybe not 10, it's maybe about 5 or 6 directories deep with their application, right? Their structure. So let's go here and say, oh, here we go. And I'm going to say here, curl localhost / that directory over and over and over. Okay. And just to be sure, real quick, just to do that, and then pgrep -u. Just showing a different way to get the parent PID or that root process PID of Apache process, right? I could definitely do this, right? But if I want to get that single one or wanted to begin to script it out, I can do that as well. Okay. Just grepping through the processes, looking for anything with the user root associated with the Apache or HTTPD process. Okay. All right, so that's refreshed there. strace-ff, actually real quick, make dir temp demo2, we'll say. And we'll do a C temp demo2, what's there, strace-ff, again, following all of the children that are forked off, -o, and we'll say temp demo2 httpd -p, that. And while we're at it, let's try this out. Right, that's one way you could use that if you want to. Again, just substituting out the output there, -p for that PID. Here it goes. Does that make sense real quick? To anybody, everybody? That pgrep there? Yeah. Okay, what I'm doing? Okay, cool. I throw some stuff up on the screen, so I'll make sure that everyone at least has an idea what's going on there without kind of just going on past it. So, cool. So, back to our demo here. Again, different from the first demo. Instead of doing that first, base root directory, now we're doing assimilating down a further path. Okay. I forget what's in this file here. We're about to find out. Okay. Forget what that is. Okay. But what we see here, again, all the processes attached. Okay. Close this off. And then shut that down. Okay, all processes detached there. Let's take a look now at that. So we are in, again, just for our purpose, we were in demo 2 already. Let's see here. Now we begin to see all of those additional requests, right? So showing this, at first customer didn't believe us that there was, by doing this one change, that we didn't change anything, adds overhead to your system. But this is a way to dig in a little further and tell them and show them, look at all the overhead you added. Now, if this is all on local drive, probably not that big of a deal. This was all over NFS. Yep. The laughs, people are familiar with NFS. So that adds the overhead quite a bit. And so after doing this, we asked them, well, do you really need those changes in HT access? And talking to them back and forth, they're like, well, really we don't. We should put them in the main config. But they won't listen to that until we showed them this. Okay. Changed it, but we put the config in the main configuration, changed it back, and they were fine, right? But I would dig in, just keep digging further and further and further, and be like, here's what's going on. Right? Here's what's happening. Now, this is one we use all the time. I said that, as well as being able to tell, hey, your process or your PHP is crashing on this process, or app is crashing on this process because it's opening this file. Again, different ways you can do that. But that same format of that following child processes has helped tremendously in our environment. In our environment, we get to see things come at us from left and right all the time. So just a way to figure out what's going on when we don't have any other tools. Okay, all right. All right, continue learning. Like I said, when I do a presentation, I like to try and have you all leave with more than you came with. Okay, I do that for presentations, for any type of training, for phone interviews. I always try to make sure that let you take away something that you can go back and try to learn more. That's what this is about. It's about learning and having a better understanding. So there is a GitHub for some small C code examples. The link there. The slides are online, but you'll find under that GitHub right there. I have them on my system already, so let's take a look here. If you clone that or just pull it down or copy it down, however you want to, you'll find something like this here. A simple file, a couple of C files, a make file, and a README. If you take a look at the README, just real quick, run the make command to build those files out. Actually, this was a contribution by someone in my presentation at Scale. I'll just run the GCC command to actually compile it. He contributed to it and said, here's a make file, have fun. It's like, thanks, it's awesome. So that was really kind of nice of him. So we do a make file, should make. What we do here is we compile out helloworld.c as well as openfile.c. Now, why am I doing this? Because if we look at the source code for Hello World, much like everybody's first application, it's very simple. It's a very, very simple C command, or C program. It says Hello World. What I want to do is tie this to what's actually happening on the system with just this simple command, or simple program. Let's take a look at that. Strace, Hello World. Okay, I'll do a -O for the output there. Did I do a start? Why is that? Well, why am I typing that many keys on it?
This is unlike Windows, it'll work if you hit start.
strace-o hello.out and then hello. Okay. Oh no, that's right. Sorry guys. It's not my path. There we go. Hello world. Simple. Okay, but that's simple. Maybe if we look at the hello world.c, 7 lines of code, some of them are probably blank, comes out to be 28 lines of system calls. Take a look at that. Okay, and I'm showing this example here because I want to show how a simple program expanded to so many different things. But when you see this in your program, they're normal, right? You become to say, hey, even a simple hello world can have something that looks something similar to this. I'm mapping memory, I'm opening files, right? I'm opening libraries. So it's a way to say, hey, this is normal. When I don't know if it's normal or not, I can run a simple program. Hey, even the most basic program opens up some of these files here, does stats on certain files. So begins to get you familiar with what output is going to look like anyway, right? Then lets you to go look for things that don't look like it should be there. Okay. All right, that's one there. Right, again, this is very simple here. We're mapping memory, projecting it, doing a stat, and then writing out to hello world. Okay. One thing that I show text here as we go through this is, right, when we say open a file, we learned earlier that format there, we have open, we have any of the arguments, and then we have the return code. Open returns the file descriptor back to the application. So that 3 there is what we use to say fstat 3, right? Fstat on that file. Okay. That's how I tried to tie into our text. That here's what's happening. The file descriptor. It's not a file name. It's just a descriptor, and then we use the rest of that throughout to either look at the file, open a file, as you see here, close the file. Okay, and then tie a little further for them. When we write to 1, what have we done? Ask text. We write to 1. What are we doing? Where is that coming from? What file descriptor is that? You know, they get to the point that they're saying it's standard out. Okay. All right. And then lastly, are obviously aggregate code. Okay. Let's take a look at the next example here. strace-o open file .out open file. This says hello world as well. So what's going on there? Let's take a look at that. Okay. As we work through here, we see here we're opening a file that's already in the directory there. Open file. We're statting it. We're reading from it. Reading from hello world. Right? We asked for 4096 bytes. We got 12. Okay. That's where they might mismatch. Where we say I want to read this much. Well, here's all I got. Here. And we move on with writing it out new line, and then closing. Okay. So again, these are just building blocks to say, let me jump to the next one and say, let me expand on these and build out, right? What is this? If I write this in my code, what does it look like on system calls? Okay. So hopefully y'all can use that. There's a URL again. And then, in closing, contact information. Same as all my presentations up there as well. Feel free to email me anytime. I'm happy answering questions. Work related, not work related. I love helping people. You know, my job here is to keep y'all entertained long enough to learn something. So hopefully I do that, and I love doing that. So I'm always out there. Short bio because my friend wrote it, and I told her I'd put all my presentations, so it's staying there. That's internal, don't worry about that. But do evaluate the one for LinuxFest Northwest. Mine, you don't have to worry about that at all. And then Q&A, or as always, talk about whiskey for our time remaining, which we got of 15 minutes? Perfect. Usually my spots are 45, so I think it's about right. So. Thoughts, questions, concerns? Question?
It's more of a comment.
Okay, perfect.
So, when debugging things like C programs, I would highly recommend you use -G so that you have debug symbols.
Okay.
And then enable the core dumps.
Okay.
Because that's very easy to investigate once you have the segment, for example. So I think when debugging things like that, that's useful.
Perfect, thank you.
And when doing Apache processes, it is also very useful to use -x, couple of x, which would make it fork just one child.
Okay.
Makes it much easier to debug.
Oh, perfect. Thank you. Appreciate that. There was -G and then -X for Apache?
Well, for GCC, that's -G.
Okay, and
And
then
debug symbols. And for Apache, it's -X uppercase.
Thank you.
One other thing is make sure you don't call strict on that binary, because then you'll strict debug symbols.
Thank you.
Or if you do, save it someplace and then.
Right, you can dynamically load them later if you want.
Yeah, thank you.
And a good session also.
Thank you.
Is there any considerations you would need to take into account if you were using, say, like Python to do a print or to do like a hello world? Like, how would that look differently than, say, your C? I mean, if you've got a little bit of
So,
abstraction there.
when it comes down to the interpretation, for Python interpreted, it's going to be the same system call at the end, right, at the very bottom. Right? There's interpretation between Python or any language into its base, right? But then all it's doing is calling what the kernel has. It is that same function.
So basically, it would look the same.
Yeah. Yeah. You might see some interpretation a little differently, but the system call should be the same. Yeah. So, obviously, you would do strace Python and then that, right? Or if it's already running strace and then run whatever Python app it is. Yeah. So, question.
So, can you talk a little bit more about the processes that are programs that don't allow strace? So, how do you say again how you do that? I mean, if you were writing the code and you didn't want somebody to do strace, and then what is I guess what were the examples that you gave that where people compile so that you can't?
Yeah. So the question. I'm trying to repeat the question here. The question was more examples about how strace. Well, how to do what to do when I can't strace, and then when developing, how to catch that, or is that correct?
Well, so yeah. So how do you said that some people make it so that strace will crash, or it was with a sig trap or something.
Yeah, sig trap. Yeah.
And so why would people do that? Or what are examples of programs that
Sure.
have that? Is that pretty?
Yeah. So the question is, what types of programs would take a sig trap and just crash, right? So usually it's things that have to do with licenses. I'll refrain from saying specific names, just out of vendors. But things that use licenses, if you're installing, right, and you're trying to figure out what the install program is doing with that license or where it's putting it, right, how it's interpreting it, maybe they don't want that to happen. Okay. Usually, it almost exclusively programs that have licenses. So maybe a Community Edition, Enterprise Edition, and the installer is a little different. You might have something there. Or if you have something that you're paying for just license or support, might be there as well. And what's happening there is that it's just taking that signal for sig trap, interpreting that as usually what you'll get a sig trap, you'll get a message stop doing this, or to the effect of, and then it will close. It'll do a sig stop, right? So when you try to trace it, they're like, no, stop it. So,
Okay.
Yeah, because all what strace is doing is sending a signal to the process, and usually that signal is interpreted as, hey, what are you doing? Here's what I'm doing. What are you doing? Here's what I'm doing, and just over and over and over. And by that nature, it adds a little bit of overhead to running processes wherever you're tracing, right? So if there's something that's super heavy and just bogging the system down, maybe not strace that one, because all you're doing is adding more overhead to that, right? If it's just a process just heavy on CPU or mainly CPU, you might have a little more overhead there. That's one caveat.
So it would be more just the install of like this license. It wouldn't be the whole install of the product, but just the install of like the license file or something.
Mm-hmm.
Okay.
That's what we've seen in the past, right? Now that being said, I mean, looking at something like what's the PHP module for IonCube for doing the never mind.
For obfuscation.
Yes, yeah. Maybe something like that might not want you to have trace as well, right? So they might do something there. I haven't tried it personally, but something like that might be an example where they're not wanting to trace that code.
But IonCube would run as a module within the Apache context, so you wouldn't really.
Yeah, it might. Yeah.
It's less relevant for that.
True.
Thing.
Yeah. Question.
So, if the program doesn't want you to strace and it like crashes and sends a sig stop, is there a way to tell if the program is going to do that before you run the strace? Because like you just run strace and you don't know and it kills the program and you're like, oops, I didn't mean to do that.
Not that I'm aware of.
Well, GDB, sure.
Well, you can do it
Yeah.
run somewhere else.
Yeah.
Just install it on some station machine
So.
and test it.
Yeah, but outside of like that one, right? Not be aware of. Yeah, JDB might do it. I'm not sure on that. I've used it a few times. JDB a few times. Like I'm on the admin side, not the developer side. So some of those tools I'm not totally familiar with. So, but yeah, maybe. Another option is LTrace. Again, that's something I've used a ton, but I've gotten feedback that's another way to look at something that's maybe not wanting you to strace it, right?
LTrace has
Yeah.
serious performance issues. Be careful. Yeah, that's what it was kind of
Cool. Questions? Yes.
Do you have any tips or tricks on S-tracing applications or processes that start and end very, very quickly to where you can't get a chance to see it in the process list?
So tips or tricks for trying to S-trace any processes that are just too quick, right?
Yeah.
So that's actually I had an issue once. It was a compromised box where the compromise part what it was doing was spawning itself over and over and over. You try kill it, spawn it, kill it, spawn it. What I ended up doing was continually LSing proc and the PID directories and just trying to S-trace everything over a certain number. Okay, that's what I was trying to do. We ended up catching it and finding out what it was doing. Found out what it was trying to we found out where it was opening from. Then we're gonna go find it there. But outside of just constantly trying to hit it, catch it, not many. Right? We've done it successfully, but it wasn't pretty. Right? It was kind of a list out over a certain number and just S-trace. Right? Or we knew it was doing PIDs from a certain range on, and so we just did a loop to say for every process here, if it's there, try S-trace it and put the output somewhere. And like I said, we try to run it 1,000 times or so, maybe caught 2 or 3 of them. So race conditions, all over race conditions. So yeah. Does that kind of give you ideas or a way to go with that? Yeah. Cool.
Next time that happens to you, use process counter.
Cause what?
Process counter. PSACCNT.
Okay, I'm not familiar with that, but I'll take a look at it. Yeah. Now I'm thinking about it, I should have looked at proc load average and see what the next one should be and just catch after that number. But process counter. Cool. Nothing else? I'm good too, guys. So, thank you.